Okay, so Earth, like the Earth rotation, okay, rotating around the sun, or it could be the rotation of the clock hand, okay, when they make one revolution, or it can be like any moving object moving in circular motion, like moving around about, or it can be the rotation of the Earth with its own axis, along its own axis, right? So any object on the Earth is rotating together with the Earth around the axis of the Earth. So all these examples, they are circular motions, right? So here in this lesson, we are going to look at what is the nature of circular motions and why should objects move in circular motion at all, and also what are some of the necessary components required to sustain a circular motion. Without it, a circular motion is not possible. Okay, now let us suppose that a particle is moving in a circular path. Before we talk about all these things, let's first understand what are some of the important terminologies, okay, the important things, such as the angular displacement, angular velocity, and linear displacement, all that stuff, okay? So suppose that a particle is moving in a circular path with a uniform velocity, okay, uniform velocity here. Right, so we have point A, and after a period of time, a short period of time t, now it has come here, point B. This is the radius of the circle, right? Same length. And particle has made a degree theta here. This is a very, very small angle, assuming that in a very short period of time, it just moved from A to B, a very short angle deflection. Okay, now first, what is angular displacement? Angular displacement. Angular displacement is just like displacement, but in terms of angle. Okay, the change in the position is displacement. So the angular displacement here is that in time t, all right, in time t, the angle made is theta. Okay, so this theta here is angular displacement, right? Now, besides that angular displacement, we have angular velocity. Velocity is a measure of change in displacement over time. So if we have the particle move in t seconds, the angular displacement is theta. Then in 1 second, we have theta over time. Okay, so theta over time is our angular velocity. We write mu equals to theta over t. Okay, or you can write d theta, delta theta, or delta times, the same thing. Right, so this is our angular velocity. So the velocity, the change in the angle per every second. Okay, now angular displacement, angular velocity, and then we have angular acceleration. What is acceleration? Is the change in velocity, right? So if angular acceleration, then it is the change in angular velocity. So we give it a symbol sometimes. Okay, it can be like some symbols are sometimes they use alpha. Okay, alpha can be angular acceleration equals to dw, d omega. Okay, and then dt here. So angular acceleration. Now, what is angular acceleration actually? What is it like? What is it like for an object to have angular acceleration? Can you imagine? For example, like when you turn on the fan. When you turn on the fan, it starts speeding, right? So the first revolution, the first 360 degree, maybe it takes like 5 seconds. The second revolution, Now it takes 4 seconds, right? Third revolution, 3 seconds, and then 2 seconds, 1 second. So it keeps speeding and speeding, and then it spins very fast. So that is an example for angular acceleration. So we said that the fan, it has angular acceleration. Okay, so the time it takes for each spin becomes shorter and shorter. So it spins faster and faster. All right. So with no angular acceleration, that means that the spinning is the spinning is the same. Okay. So that is angular acceleration. Right. So from this diagram here, let's just say that for a very small time period, okay, we take this out, we take this part out, I can draw a triangle here. Okay, so we draw like this, something like this. For a very small change in time, we have radius, and then we have displacement. What displacement is this? We have our angular displacement, this one, right, theta. But what this displacement is this? This is, we call the linear displacement. Okay, linear displacement. So we got two. One is angular, and another one is linear. And this linear displacement is very, very small, such that it is almost like straight line. Okay, so let's just put S here, displacement S. So we want to know here, what is the relation between the two, between angular displacement and also the linear displacement? What is the relation between these two? All right, using geometry, the rules of angles, okay, we know that S, this is the length of arc, right? Circumference, S equals to R theta, right? It's like apply for a sector of a circle. So don't forget our theta here is in radian, okay? So S equals to R theta. This is the first one, the relation between my linear displacement and my angular displacement. Okay, if I divide this by T, so we have S over T equals to R theta over T. Then what do we get? This one, displacement over time, we get velocity, right? But this one is linear velocity, because here we get linear displacement divided by time, we get linear velocity, okay, expressed as V equals to R, and then again, I have theta over time, this is my angular velocity. Okay, so V equals to RW. This is, don't forget, there's two, the difference, one is angular and one is linear. What does it mean by linear? Linear, the direction is along the, is like tangential to the circle, to the circumference. Okay, the velocity is tangential. What does it mean by tangential? If you draw a radius like this, right, then the velocity direction is 90 degrees to the radius here. It's tangent at this circle. So of course, when you move to the second point, point B, then the direction change, right? Now it is pointing in this direction. Okay, V and V. Now for magnitude, it's the same because it's a uniform circular motion. The speed is the same, but velocity is different. We will talk about this in the next slide, right? Why is velocity different? Okay, so for now, is the formula. So V equals to, this one is the second one. And then again, I divide again by T, V over T, RW over T. This one we get, what is this? Acceleration, right? Acceleration. So what is acceleration? Is this? This is linear acceleration. Okay, linear acceleration equals to R and then alpha. And here we have our angular acceleration. All the components of linear and angular here, they are related by these three equations. 1, okay, 2, and equation number 3 down here. Please remember the relation between the angular and the linear. Okay, so they are all vector quantities. Okay, they are all vector quantities. Angular acceleration, velocity, or linear acceleration, velocity, they are all vector, meaning that they have direction and magnitude. Now, here's a question. Where is the direction of the linear quantities and where is the direction of the angular quantities. For the linear, we have talked about it. It is tangential to the circumference here, right? So all this displacement, velocity, linear, the direction is, it changes, right? It changes, but it is the tangent to the circumference here. So these are the linear direction. How about the angular? Where is the angular acting? If I want to label the angular, let's say the angular acceleration, how do I label it? All right, so where is the direction pointing? Now, understand this. The circle that you are looking at here, it has a axis, okay? It has a rotational axis, okay? The axis align where the body is rotating around it, right? And the axis, where is the axis? The axis here is the center. Imagine the center, and then the line is pointing towards your face, okay? It sticks out from the screen. So the circular motion is controlled by this axis. This is a very important axis because it controls the circular motion, the direction of the circular motion. Okay, you can think of it like an umbrella. The umbrella on top is circle, right? And then you have the handle at the center. And then you hold the handle, right? So if somebody asks you, okay, move your umbrella over here because there's rain coming from this side. How do you move it? You take the handle, you swing it to the left side like this, right? So you are moving the axis, you are moving the handle, and then the whole umbrella, it follows like this. So you are moving the axis that controls the direction of the circle. Okay, so that side, I move it there, I move it here. So I'm just controlling the axis. So the axis become a very important axis for a circular motion because it controls the direction of the circular motion, right? So we have something like this. If I want to draw it in 3D, right, then you see something like this. This is a circle, and we have the axis going through from the back and also the front. Okay, now this axis here, this is the circular motion, right? Isometric view, isometric view, so 3D view. Now, where is the angular direction, the angular velocity, the angular acceleration? Understand that they are all along the axis. The direction for the angular characteristics, all the components, they are acting along the axis. Okay, along the axis. Now, don't confuse with the motion of the particle. Okay, the motion, where is the particle moving? The particle is moving along this path, right? Along this path. So the particle is not moving along the axis. So angular direction does not tell where the particle is moving. The particle is moving together with the linear velocities, all that. Okay, but angular is along the axis. So here we understand that all angular quantities, okay, let me write this down here. Quantities have direction along the axis of circular path. Okay, any circular path, they must have an axis that controls the circular path. Right, so that is the difference between the linear and the angular component. So some basic terminologies that you need to know before we go to the next part, okay? Right. For the next part, we will talk about one very important component that always happen together with the circular motion. Without that one, a circular motion is not possible. Okay, that is the centripetal acceleration. Right, now you can take a screenshot of this one. I will erase this and I will move to the next slide. Okay, so why should an object move in circular motion? It is because of one thing. and it is because of the centripetal acceleration. What is centripetal acceleration? Okay. First thing, speed. When an object moves in circular path, the speed is uniform, meaning that the speed is the same. Understand that speed has no direction. We are only talking about magnitude. So the magnitude is the same. So if the object move here, let's say 5 meters per second, right? So the speed over here is also the same. 5 meters per second. Over here is also 5 meters per second. The magnitude is the same. Can the velocity be the same? Velocity has direction and magnitude. So direction is included. Now, when you draw the direction of velocity, linear velocity, okay, suppose that particle move from this point to this point, r, and then this is the angular displacement. The velocity vector at here is pointing like this, linear, right? So tangential velocity. And the velocity vector after it has gone to this point, tangential to this one. Okay, let's just say that this is v1, v2. Now, in terms of the magnitude, they are the same. Speed is the same, but velocity is not the same. Why? Because the direction is different. Okay, the direction is different. Now, if the velocity is not the same, then what does it mean? If velocity is not same, meaning that we say that there is a change in velocity. Okay, when the particle moves from this point to this point, it changes velocity because of the direction, right? So it changes velocity. So if there is a change in velocity, then acceleration has to involve. Acceleration has to involve. So there's an acceleration here. Acceleration involve. What acceleration is this? Our velocity is linear velocity. So the acceleration due to this velocity is also a linear acceleration. Okay, so acceleration involved and that is linear. So there is a linear acceleration due to which particle is changing its direction, changing its speed. Okay, question. Where is this acceleration acting? Okay, and how do we find it? How do we create it? We create this acceleration by changing the velocity, right? So where is it acting? Okay, using geometry from this diagram here, we take the two vector out. Vector 1, v1, and vector v2, like this. v2. Okay, so here, understand that the angle, this is the radius, right? This is radius, let's say radius line number 1. And v1, they are perpendicular. Okay, because tangent. And then after the angular displacement theta, the r got here, right? R2. And then with v2, then this r2 is perpendicular to v2. Follow the rule of angles. Whenever it makes a deflection of theta, the tangent also make the same deflection. Okay, when r1 goes to r2, it makes a deflection of theta, this one. Then their tangent, which is v1 and v2, also have the same angle. So the theta also here, theta. Okay, so theta here. So I can put the theta here. v1, v2. And this theta is a very small angle. Okay, now from here, we find out where is the direction of the acceleration. Acceleration equals to change in velocity over time. So if initial velocity is v1, final velocity is v2, change in velocity, final minus initial over t. Okay, v2 minus v1. How do I find it? Using vectors, right? So your v1 is pointing up, right? What is minus v1? Minus v1 is pointing down like this. This is minus v1. Okay, v1 and minus v1. And then v2 is same. I don't change the direction. I just do it like this, v2. Okay, think of it like journey. I start here, and then I go down, I go here, I end here. So if I draw a shortcut, then the arrow would be pointing to the left from here to here. And this is expressed as negative v1 plus v2. So that is also same as v2 minus v1. So v2 minus v1, this vector is represented as this vector here. This is v2 minus v1. In other words, that means this is the direction of our linear acceleration. It is acting here. Okay? Where is this direction? How do I relate with this diagram here? Okay, I know it's pointing to the left, but where is it? Right? So now, the angle of a triangle, 180 degree. Okay, the sum of interior angles. And also, we know that the length of these two, v2 and v1, is the same. Why? Because the magnitude is the same. Okay, the speed is the same, right? So magnitude is the same. This v1 and v2, they should have the same length. That means we get an isosceles triangle. Okay, isosceles triangle. If the angle is very small, that means the angle at the other two corners, this one and this one, add up. Okay, they are the same angle because it's isosceles, and they are approximately 90 each. 90, 90. Okay, assuming that this angle, very, very small angle, then we have 90 this one and 90 this one. So they add up 180 degree. Okay, so that means the angle between v2 minus v1 with the vector v1 over here, this one, we label this, the blue one, okay? The angle between here and here is 90 degree. That tells you the acceleration vector is perpendicular to the linear velocity vector. Whatever is the linear velocity vector, the acceleration vector is perpendicular to it. Okay, so here at point A, where is my linear velocity v1? Okay, where is the acceleration acting at this point? It is along the axis of the radius, along the radius like this, same as the radius. This is the acceleration. What acceleration is this? Linear acceleration. Okay, it has gone here, point B. Again, show the direction of the acceleration, centripetal acceleration. Okay, again, it's along this line A here. Every point on the circle, the acceleration is pointing towards the center, regardless of the positions. Okay, the acceleration vector is always pointing towards the center. That is why we call it centripetal acceleration. Without this centripetal acceleration, the object will not go in circle. How will it move if suddenly the centripetal acceleration disappears? You see, here, we start by drawing this one. Initially, object move like this. Okay, so this is the velocity, velocity vector. Then there's a change in velocity, right? Change in velocity, that means acceleration lah, perpendicular to this velocity vector. Okay, so the new velocity would be now over here. Again, there is a change in velocity. So acceleration perpendicular to velocity vector. Now the objects move in this direction. From here, oops, it goes in this direction. Again, there's a change in velocity. Okay, every time it moves along the path, there is a change in velocity. So the acceleration always acting on the object. What acceleration? Centripetal acceleration. Right? So we have another change in velocity like this. Okay. And then you get something like this, new velocity like this. Okay, over here. You can keep on doing this, and then you find that you get a circular path like this. Okay, you get a circular path. It's because of what? It's because of the acceleration, this one. If suddenly there's no more acceleration, this blue arrow suddenly disappear. Where will the object go? The object will continue to go straight in a straight line. And then it's no more moving in a circular motion. If this acceleration stop acting. So that means to sustain a circular motion, acceleration always have to be there, right? Always have to be there from time to time. And also I have made this vector very big, right? If you make the vector very small, meaning that you take a very, very small change in time, then you will get a perfect circular motion. Okay, yeah? So what is the magnitude of this acceleration? So we have so far understand the acceleration and what causes circular motion, and also where's the direction, all that. Okay, yeah? Now for the next part, this one, how do we find the centripetal acceleration? How do we calculate it? Huh? Okay, so here I write centripetal acceleration. Okay, we do a simple derivation. Here we have talked about the triangles, right? So we have first the triangle, this one. This is the theta. We have radius, and this is the linear displacement. Okay, and then we have another triangle. That is the velocity vector. Huh? We have VV. This angle is the same as this angle here. And this one, we have the change in V. That is the acceleration. Okay, this triangle is here. Taking the two triangles, similar triangles. They are both isosceles triangle. And they are similar. Why similar? Because isosceles and plus their angle is the same here. So they are similar triangles. Similar triangle means that the scale, the proportion is the same. So I can write S over R equals to change in V over V. Okay, I can put like ds. Okay, ds and change in S, change in V like this. Okay, so this is based on the similar triangles. Right, so ds over R equals to change in velocity over V, and then we divide by the time. Just put the time in lah. Change in time, we have R equals to change in V, change in time, V. What do we get? This one is linear velocity over R, and this one is linear acceleration over V. So you get A equals to V squared over R. This is the formula. Let me box this. So take note of the one that I boxed. You might want to remember some of the formulas, okay? They are the formulas that usually you will use in calculations. Okay, so A equals to V squared over R. This is the linear centripetal acceleration. What is this is magnitude, right? What is the direction? Towards the center. Now, besides from this one, also we have some other things that the question will ask you to calculate, like period. For example, like period, okay? What is period? Period is the time taken in one cycle. Okay, time taken in one cycle. We know that angular velocity is theta over time. Considering that it moves one cycle, so 2 pi. The time used to move one cycle, we call it period. So I substitute this with capital T. That is the symbol of period. And then we have period equals to 2 pi over. This one also, you might need this. And also frequency. Yeah? So frequency is the inverse of period, right? So frequency is 1 over 2 pi. So angular velocity can also be expressed as 2 pi f. Again, I box this one. Right? So just like the satellite, how it rotates around the Earth without falling down, or the moon revolve around the Earth and not falling down. Why? It's because of this, because of the linear velocity. So they are moving, which keeps them up there. So the gravitational force pulling it down is being cancelled by the linear velocity. Okay, every time it tries to pull it down, then it continues to move in this direction. It tries to escape. Okay, it tries to escape. Because of the gravitational force is balanced by the speed. So there they find a balance, so it's moving in a circular motion. Also because if there was no centripetal acceleration, then it will be thrown off course like this. Okay, it will continue whatever direction that it is moving initially. Okay, so like this. How do you, for example, how do you decrease the altitude of a satellite? Okay, you just decrease the speed, right? If you decrease the speed of the satellite, then it goes spiral inwards like this. Because when satellite loses speed, it loses the linear speed, then it starts to curve inward. Okay, so how does it maintain same altitude? It's because the linear speed. There is a minimum required speed for it to stay at the same altitude. This we will discuss more in the gravitational lessons, okay, gravitational force lessons. But here, let's just stay in the circular motions. All right, so you can take some notes and I will go to the next slide where we will talk about the next one is what create this centripetal acceleration. Like a motorcyclist, if the motorcyclist want to turn, he has to adjust his body to get the centripetal acceleration. How does he get this centripetal acceleration? From where, right? So he has to manage his body posture, he has to manage his body positions, okay, to create this centripetal acceleration. So you have learned that whenever there is acceleration, there is a force, right? There's a resultant force, F equals to ma. So same for this one. If there is centripetal acceleration, there must be force somewhere that creates this centripetal acceleration. And for the next part, we will look at this force that we call the centripetal force. All right, so I'll go to the next slide. Okay, force in circular motion. Now we have understood that force can do a few things, right? If you have an object moving in this direction, force acting along with it, same direction with it, it can speed up the object, or it can start a stationary object. If my force is opposite to the direction, then I can cause retardation, deceleration. The third use of force is that I can use it to create circular motions. So very simple. Okay, first, what is the natural motion of body? The natural motion of a body, let's say I have a body, right? I just leave it, like I just tell the body, okay, you can move however you like. Okay, how will it move? The natural motion is straight line, right? Straight line. This is back to the Newton's law, inertia. So if you don't disturb the object, it will continue to move in a straight line until there is a resultant force. So the natural motion of every object is a straight line. Now, I can change from linear straight line to circular motion by applying a force that is perpendicular to the speed component. So suppose that the object is moving in this direction. I act a force perpendicular to this velocity vector, then how will it change the motion of the object? Here, it is moving in this direction. So I apply a force, pull it down. So now it moves in this direction. Okay, now again, I continue to apply the force, pull it down, and now it moves in this direction, like this. So the force that apply must be continuous. Okay, it must be continuous here. From here, here, force is in this direction, perpendicular to the vector. Continue to apply. Now it got here, here. The force is here and here. Okay, so again, this vector is a very large vector. If you make it very small vector, you get a circular motion. Why is object moving in circular motion? Because there's always a force acting perpendicularly. Okay? There's always a force acting perpendicularly to the direction of the velocity. So with this force, I can change straight line into circular motions. Now, if you see the direction I draw here, all the directions of forces, they are pointing at the same point. Extend all this, they are pointing at one point at the center. Okay, just like our centripetal acceleration. This force is the one that creates the centripetal acceleration. Because it points towards the center, we say that it is a centripetal force. Okay, centripetal force. Without centripetal force, there cannot be circular motion. The Earth rotation, it has to have centripetal force. The moon rotation, it has to have centripetal force. Even the clock hand, also it must have centripetal force. A spinning pendulum, it must have centripetal force. If I withdraw one force, then it will move in this direction and it will destroy the circular path. So we say that these two, the centripetal force and circular motion, these two twins, they are inseparable. Okay, they are inseparable. Two of them has to be there. Okay, so understand that. And also, how much is the centripetal? How do we calculate this centripetal force? Okay, so we know F equals to ma, right? So F equals to ma. Applying this centripetal acceleration is v squared over r. So we have F equals to mv squared over r. Just add an m there. Right? So since v equals to r omega, then we get F equals to, okay, v squared equals to r squared w squared. This is r squared w squared over r. So we have mr w squared. We get a second formula for centripetal force. Please take note this two. You are going to use two of them. In some cases, you use this one, in some cases, you use this. Whenever the answer, sorry, when the question asks you to calculate like angular velocity, okay, you use the second one lah. And the first one is for the linear velocity. Both are the formula for centripetal force. Okay, so if a motorcyclist want to turn roundabout, okay, let's say, then he has to create this centripetal force by rolling to one side. Okay, we'll discuss a few of the examples after this. Okay, like a motorcyclist roll to one side so that the reaction force change, and from there it produces a centripetal force that allows it to move in circular motion. Same as an airplane. How does an airplane turn? It will bank at one angle, tilt to one side, it will roll to one side, so that the lift force initially is pointing straight up. Now it is deflected. So it has got, from there, it creates a centripetal force by managing the orientation, the positions, okay, of itself, of its own positions. We're going to have a very short break, 2 minutes, and then we will come back and continue again. So we'll come back at about 7:48 lah, 48. Okay. Okay, guys, we are back. Let's continue on. Okay, the banking of a curved road. For a vehicle to turn, it has to create this centripetal force. And if the road is level, okay, if the road is horizontal level, then the centripetal force is created from friction. Just like a car, to turn, it has to apply friction on the tire. And that friction creates the centripetal force if the road is level, right? So what is the drawbacks of this one? If the car wants to move at higher speed, then the friction will become bigger. So high friction, okay, it will cause the tire to wear out quickly. That is why in some of the, you may have seen in the car racing or in the test field, they have this road which is raised from one side so that it makes an angle, like tilting. Okay, so this is, we say, the banking of a curved road. Okay, now how does this help in for the driver to move at high speed? And what does it do? What is the purpose of raising this level here? Okay, it's all due to the, again, the circular motions and the centripetal force. Okay, you see. Now, assuming that it is raised by an angle theta, we have the forces mg and reaction. Extend this one, we have the same angle here, theta. Extend here, this is also theta. Okay, so reaction force. Resolve the forces into horizontal and vertical components. So we have r cos theta, that is the vertical, balanced by the mg. And then we have r sine theta equals to, now this is the horizontal, right? Horizontal forces. Assuming that from the incline of the road, the car does not need to apply any friction on the tire to turn. Okay, normally on a level road, it has to apply friction to turn. But since we have an incline, a bank road, the car does not need any friction to turn. So the horizontal forces are all due to the reaction here. R sine theta is equals to the centripetal force, mv squared over r. Okay, so equation 1, equation 2. Now we have equation 2 divided by equation 1. We get tangent theta equals mv squared over mgr. Okay, we can cross this. Tangent theta equals to v squared over gr. And please remember this does not only apply in this case, it also applies in like a conical pendulum. Okay, a pendulum where it moves in horizontal circular motion, or a ball moving in a ball. Okay, later we'll show a few examples of that. Also, it'll be in your exercise. This is like a more general one. Okay, so this is the derivation. Tangent theta equals to v squared over gr. What is the v again? The v is the linear velocity. Okay, linear velocity. Okay, from here, I can express this as v equals to square root rg tangent theta. Okay, so what is this? What does this tell us? Depending on the angle, the banking angle, okay, given the angle here, it is expected for the driver to travel at this average speed here. Okay, if based on whatever angle you put in here, let's say you calculate the speed and then you get v, the speed. This speed is the correct speed for the driver to travel at to produce no friction at the tire. Okay, so if the driver move at this speed, then there will be no frictions acting at the tire. So if the speed that the driver traveling at is higher than this expected speed, then it needs extra inward friction. Okay, yeah. So you can think of it like the minimum speed to have no friction acting on the tires. Okay, the minimum speed. If he travels faster, then he needs extra frictions, inward frictions to help him maintain this circular motion. Yeah, so this is minimum speed to move in circular path. And also, if the angle is high, what does it tell you? If the angle is high, then the centripetal force is high or is it low? Sorry, not centripetal. Let me rephrase. If the angle is high, the frictional force is less. Friction required is less. That means it can move at higher speed with no friction, and also less likely sliding will occur. Okay. So the application of this one in the real life situations where they curve it, they raise from one side, they increase. The more the angle, the less likely will be the sliding. Okay, occurs. All right, other similar examples like this one. For example, like the airplanes. When the airplanes roll to one side because it wants to turn, the turn in a circular path, we have the forces mg. And again, because airplanes is up in the air, so there's no reaction, right? There's no in contact with any surface. So it's just lift force. L is the lift. Okay, L. And it's the same. If you derive the equations, you get the same thing, the same result as this one. So this also applied for the airplanes. Or it can be like a ball moving in a horizontal circular path inside a bowl. Okay, like this, it moves in a horizontal circular path. It's the same applications. Here, if you focus only on one side, let me blow this up. This side. So this is the surface. This is the ball. The forces, right? So we have mg. Where's the reaction? This is a curved surface. So normal reaction somewhere here, R, like this. You see, again, R is sloping and mg is straight. So you derive the equation, you get the same result as this one. So same tangent theta equals to v squared over gr. Or it can be like a conical pendulum. Okay, you tie a thread to this point, and then the pendulum is allowed to move in a horizontal circular motion. Yes. But only the forces is different. In this case, it would be mg, and then we have tension, right? Instead of reaction and instead of lift, we have tension, T. Or it can also be like you put a coin or anything on a rotating disc. Say we have something that, a flat disc that rotates. Okay, so you put a coin here. What is the minimum speed to keep the coin in rotation? Okay, without flying out. All this we can calculate using this formulas. Okay, tangent theta equals to v. So, but for this one, right, it's a bit different. You see here, all the examples here I show is the forces is tilted, is sloping. Right, the curved rope, reaction force, and the lift, the tension, But for this one, where is the normal reaction acting? Normal reaction is acting vertical up. Normal reaction. And we have the mg. Now, if I spin this at a certain angular velocity, will it keep moving in a circular manner? Okay, all this we can calculate. But the force here, reaction is vertical. Then what is the centripetal force that it used to keep it in circular motion? It is the friction. Okay, friction. Just like the turning car on a level road, it uses friction to help it. So same as this coin here, it uses friction to keep it in circular motion. Okay, yeah? So this is static friction. Static friction. So sometimes from the question you'll see that static friction equals to what? Coefficient over coefficient into the normal reaction. We can calculate this. Okay, so here for the coin, the centripetal force can be expressed as F equals to mRW square. You got 2, right? Or you can put it as mv square over r. And here the friction is the centripetal force. But for this one, the car moving at the curved road, the centripetal force, okay, here is different. You have to resolve it, right? You have to resolve it. Okay, here. From here, F equals to mRW square. You can see that the centripetal force depends on what? Depends on the radius, depends on the mass, and also depends on the angular velocity. Assuming that we have the same coin here, and I slowly increase the rotation of the disc, the angular velocity of the rotation. What happened to the coin? What happened to the friction needed to keep in circular motions? If the angular velocity is high, if it increases, then it will need higher centripetal force to keep it in circular motion. If the friction does not meet this requirement, then it will be thrown off. Okay, it will fall off. Right? So if you increase the angular velocity of this one, then you have to make sure that the frictional force is able to keep up with the increase in the centripetal force, which is the force needed to stay in circular motions. So questions normally they will ask you to find, okay, what is the minimum force, okay, required to keep it in circular motions? Okay, we'll look at a few after this in the past year's questions. Right, so that is for this small part, one of the application of circular motions. Next, we look at vertical circle. Okay, all these, they are horizontal circle. Movement, circular path along the horizontal plane. Okay, along the horizontal plane. And for the next part, we'll look at when object move in the vertical plane. It's also circular motions. Okay, an example, like a car, a trolley, or anything move in a vertical loop. Yeah, we take 3 positions for this one. Now we are talking about vertical circle. Vertical circle. Vertical circle means that sometimes the force might be against the weight. Horizontal is independent, right? If you move in horizontal, the weight is always vertical down. If you move vertical, then at some positions it might be affected by the weight. Okay, let's take 3 positions. We have first the trolley here, and here, and also at the top. This one we don't really do it because it's the same as this one. We don't really need to do this. Okay, only 3 positions. All right, so mg. Now it is moving inside, right? It is moving inside on the track. So that means there will be reaction. Okay, there will be reactions. So where's the reaction pointing? It is inside the track, so the reaction is pointing inward. R. From here, at this point, centripetal force Fc equals to, okay, R bigger than mg. So centripetal force equals to R minus mg. Okay, so you should have a resultant pointing to the center, R minus mg. So I can write it as R equals to centripetal force and plus mg. This one you can move it like mv squared over R plus mg. Okay, we get this here at the bottom. You find that the reaction at the bottom is much greater than the reaction at here, at the top, at the side. Okay, why the reaction is much greater? It's because of the weight is acting against it. The weight is pulling down, right? So the more weight is pulling it down, the reaction will become higher. So it's like the weight is hindering the reaction. Okay, so here you can just think of it like conceptually. Okay, so without the derivation, you also can think, okay, common sense, this one, the weight is going against me, then my reaction should be higher here. Now, if it was a string, it's the same thing. Okay, if it was a string, then you do tension. Okay, it can be like a string hanging a pendulum, any masses like this. Okay, such that I rotate it vertically like this. So if it was a string, then you have mg and you have tension. And this tension at this location at the bottom is the highest compared to the tension at the side, at the top here. Same with the reaction. So when the string snaps, usually it will snap at the bottom. Right? You spin it until this point at the bottom, it snaps. Because this is where the highest tension is acting. Okay, here at the side, right, my reaction is towards the center, R, and then mg down. Centripetal force here, Fc equals to reaction force. So I can write R equals to mv squared over R. So the mg is independent, is irrelevant. And as it come here, the top, then we have R downward, mg also downward. Okay, what's my centripetal force? Equals to mg plus R, the total of the two. Okay, then if you arrange this, you get Fr equals to Fc minus mg. We have mv squared over R minus mg. Reaction is the smallest at the top. Okay, reaction is the smallest at the top compared to this 2 point here. Why? Because think of it like the mg is helping you, right? It's helping you, it's contributing in the centripetal force. It's pointing down here. Down here, the mg is hindering. Here it is helping. Okay, so that is why the reaction up here is the lowest. It is the lowest. Right? So here for the string, same. Tension is the lowest up here. Tension. This one is in between, and this one is highest. Right. So this is some key things to take note for the vertical loop. For the last one, we'll talk about the Earth rotation. Okay, I'll go to the next slide. Give me a second here. And also, sometimes the question will ask, what is the minimum speed? Like, for example, at the top here, point A, B, C. What is the minimum speed to continue to move in circular motions? Okay, we can, our formula from the previous slide, V equals to RG tangent theta, right? So in this case, in the vertical loop, what is this data here? For the horizontal circle, let's say this is your object moving in a horizontal circle, the centripetal force is pointing, let's say, to the left, okay, horizontal. And then your reaction, it could be reaction, it could be tension, anything, is making an angle with the centripetal force. This angle is this angle here. It is the banking angle. Okay, it is the banking angle. Now, don't confuse if you are dealing with a circular, a vertical loop. This is for horizontal loop. Huh? So the angle is like between the centripetal force and the reaction that is tilted. If you have a vertical up here, what is that angle? This, the reaction force, right? For this one, the reaction force is parallel to the centripetal. They are on the same plane. This is different. They are not on the same plane. This one is on the other plane. The centripetal is on the other plane. It is the angle that they make. But for this one, vertical, up here, reaction force, same plane as the centripetal force. So the angle between them is 0. Okay? Same for this one, here, 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 and here. Okay, yeah, so something to take note for this one. Okay, last is the Earth rotation. Circular motion of object on surface of the Earth. What time is it? 8:12, right. Right, so suppose that we have an object, okay, on the surface. So any object on the surface of the Earth, they are moving in circular motion together with the rotation along the axis. Okay, so we take horizontal motion here at the equator. Okay, so object A is rotating along the axis of the equator. Now, same thing. If I draw the 2D diagram, let's say I draw a 2D diagram, this shows the top view. Imagine that you're looking from the top. Okay, you're looking from top here. And this line is the equator. Okay, so our object A is here, moving along the equator. Identify the forces, right? So we have the center, gravity, mg, inward. And because the object is located on top of the surface, right? It is not located inside the Earth. It's outside. So the reaction is pointing outward. R. Okay, reaction is pointing outward, not inward. That is for rotation on the surface. But now this mg, sometimes if they give you the mg, the gravitational force, right, it can be expressed as mg, or sometimes you will see this as the gmm over r squared. This is another formula for gravity. This one we'll discuss more in the coming lessons, gravitational force. Okay, but this, sometimes you see this is also gravitational, the gravitational force. Okay, now, so we have R mg, centripetal force Fc is equals to, we should have a resultant acting inward, so mg minus R. Or you can write gmm over r squared minus r. That is also correct. Okay, so mg minus r, then we get r equals to mg minus centripetal force. I can express it as mg minus mr w squared r. This is to find the reaction acting on the object, the reaction, okay, acting on the object due to the rotation of the earth. At any point is the same. This point, this point, this point, the reaction is the same. It is along the equator, right? Because the radius here, we take the radius the same over here, 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 and here. Now that is different when you have the object up here. If the latitude is different, if the latitude is here, up here, then your circle is this one, much smaller. Okay, your circle is this one, much smaller. So the radius change, and then the reaction also change. Right? Down here, same. If you're rotating here, if you're located here, then you spin, then you're moving along this axis, not the equator. So this one have a different radius and has a different reaction. You can see reaction depends on the radius. Okay, so conclusion is that on the rotation of the earth, depending on where are you located, reaction is different at different locations. Okay, different at different locations. How about at the tip here, at the North Pole? At the pole, is there any rotation? There will be no rotation, right? There will be no rotation at both the pole. So if there's no rotation at both the pole, then what happened to the centripetal force? There's no centripetal force, there's no centripetal acceleration. Okay, acceleration centripetal is 0 up here, down here. Any object you place it here, it will not move in circle. Okay, now here, what is the angular speed? Let's say the question asks you, what is the angular speed for the object to feel weightless? To feel weightless. Using this formula, we can find what is at what rotation speed, okay, the object will feel weightless, at what rotation speed of the earth, right? So to feel weightless, the reaction is 0. Okay, because if you feel weightless, that means no force acting on you, no reaction. So R is 0, right? So if I put in here R equals to 0, then I get mr square equals to mg. Then I can cross this, r square equals to g. Calculate this, equals to g over r. This one, you know, 9.8. What is the radius? What radius is this? This is radius at the equator. You can just take the radius of the earth. Let's take as 6.4 times 10 power 6 meter. Okay, so 6.4 times 10 power 6. Put it inside, calculate this one, and you get 1.23 times 10 minus 3 in radian per second. Okay, angular in radian. per second, and you can change the degree to find how much is the rotation of the Earth to feel weightless on the object. Okay, so at the pole, is there any reaction? Yes, reaction equals to, okay, our formula R equals to mg minus mr w square, right? So at the pole, this one is 0 because no centripetal force, no centripetal acceleration. So at the pole, R equals to mg. Reaction at the equator, at the pole, is different. Okay, so I write down a few things to take note now. So reaction at pole and equator is different. And also centripetal acceleration at pole is 0. Right, take a rest and I will send you the exercises. All right, guys, you can start doing. We still have like about half an hour. You can take the time. Any questions you can ask. Number 3 can do or not number 3? Try number 3. If we look at number 3, and the rest you can do it yourself. An elastic cord has an unextended length. Okay, so original length of 13 cm. One end of the cord is attached to a fixed point C. A small mass of weight 5 Newton is hung from the free end, and then the cord extends to 14.8. Right, so when you put the mass 5 Newton, there is an extension X. Okay, now B1 show that the angular speed of the cord and the mass is 8.7. Right, so basically, like you have this cord, you rotate it, vertical circle motion. Okay, so they take the point at the top. What happened to the tension at the top? Now, at the tip, at the highest point, the tension is 0, same as reaction. Reaction at the top is also 0, because at the top, all the centripetal force is from the mg. Okay, from the mg. So here, the tension here would be 0 temporarily, okay, only at this instant. And as soon as it drops, then it starts to rise again, and maximum at the bottom, right? So we have mg is equals to the centripetal force. Okay, so we can write F centripetal equals to mg, that is mr omega square equals to mg. Cancel, cancel, and you can find the angular speed. G over R. Okay, and you should be able to get this 8.7 radian per second. Right, for C, how about, sorry, not C, B2. How about B2? The question asks, calculate the length of the cord assuming that it obeys Hooke's law. Okay, calculate the length, okay. Meaning that we want to find L. Now, first note the position of the pendulum, okay, of the mass. The position is like at the bottom, okay, at the bottom. So we want to calculate this L here, and at this instant, it is at the bottom. Right, so at the bottom, then you know that at the bottom, what happened to the tension? Tension is upward. We have mg downward. That means centripetal force is tension minus mg. Okay, so we have mr omega square tension minus mg. Yes, this is the equation we use to find the angular speed. So we want to find this, meaning that we need to know the m. Okay, we already got the m, we got the weight, we can just divide by the g. Radius at this position, what is the radius? The radius is L. Okay, is an unknown, so you put L inside, and this is what we want to find this. And also, sorry, this one is given, right? We want to find the L. This one is given, so we use the answer from A, which is 8.7 radian / second. Okay, so from here, where do we get the tension? The tension is the force pulling the string, right? Pulling the cord. So how do we get it? From the Hooke's law, F equals to kx. First, you have to find what is k. That is why they give you the length here. Before you put the load, it is 13 cm. After you put the load of 5 Newton, it is 14.8, right? And then when you spin it at the bottom, that is much longer, L. Okay, we want to find this. So from the first two, we get the spring constant first. Okay, so K equals to force equals force over x, that is 5 over the extension minus it, we get 1.8 times 10 to the power of -2 is, if I put it in meter, okay, equals to, I'll just leave it like this. Okay, so I don't have to write too many decimal numbers. Right, so 2500 over 9, that is our K value. Once you get the K, find the extension. So using again Hooke's law, okay, force of 5, and then this one, the force, this force is the tension, right? This force is the tension pulling the string. Okay, we have K. X is when it is at this position, X is the length minus our original length, which is 13. So L minus 0.13. That is my X. My equations, I write it here. F equals to Kx equals to 2500 over 9, and then this is L minus 0.13 equals to the force pulling the spring, F. Okay, this is the tension. Okay, not 5 Newton. This one is not 5 Newton because 5 Newton is the weight of the object, right? So we are doing the tension. Because when it is in motion, right, the tension will change when it is in motion. If you are just holding it like this, then the tension is the same as the weight. But if you are swinging it, the tension is different. So this force is tension. So we have equation 1. This one we put in this equation. Then we can find what is L. So you solve it algebraically, you will have L, only one unknown in the equation. Okay, you are able to find what is L.